We'll be testing if the quiet kernel parameter improves the Linux boot speed. Then we'll look at the Linux source code just to see what it does when you provide the quiet parameter. Now, to preface, quiet is a kernel parameter which makes the Linux kernel not output any text during the boot process. Some people say that this will improve boot time just because the kernel doesn't need to print anything anymore. Now, as for how I tested this, I used a tool called systemd analyze, and after booting, the kernel time specifically was measured. I am using Arch Linux 6.7.9-Arch1-1 on an AMD 64 CPU. I had 10 trials when quiet was set and 10 trials when quiet wasn't set. Hopefully that data is sufficient. And as for the data, I wasn't able to tell a statistically significant difference between booting with quiet and booting without quiet. But now, let's look at the Linux source code just to see why this might be the case. To download the kernel, first go to kernel.org and then click the big download button. Then use a utility called tar to extract the Linux source code onto your computer. So here I have two instances of the Linux source tree. I'll use the one on the left to view files, and I'll view the one on the right to grep for specific text. Now, where the interesting part is, or where you want to look initially, would be in a file called main.c in the init folder. So this is basically where Linux starts up outside of very architecture specific boot code, like assembly. The interesting function you want here is called start kernel. This is one of the first functions that gets ran in Linux, so it's where interesting stuff happens. So you'll notice, what the kernel uses to print text is this pr_notice function. So that function is interesting and we are probably going to investigate. Firstly though, it does do things with the quiet parameter in this file. If you search for the text quiet, you'll see these interesting lines here. This is the part that says, hey, if we have the quiet parameter, if that's being called, run this function. If we look at the quiet kernel function, when you run the quiet kernel function, it will set the console_log level, which is a global variable dictating your console log level, to console log level quiet. So now we know that there's some kind of console log level variable which is being set when you set the quiet kernel parameter. Let's see how and why this is being used. So let's see how exactly pr_notice is defined. So it's defined in include linux printk.h. Let's go there. On line 519. So all this does is calls printk with the kernel_notice level and then your formatted text. So let's look at what the printk does. Either feeling like it'll be in this file. Yep. So what printk does here is it basically just calls into another macro, but what's interesting here is this _printk function. We can find the _printk function in kernel/printk printk.c. So this is the printk function. All it does is starts doing variadic arguments for the string formatting, then it calls vprintk. So let's see exactly what vprintk is. So vprintk is defined in printk_safe.c. Here it is here. Basically, it'll either call vprintk deferred or vprintk default, depending on whether or not there is an active print lock. A print lock exists so the kernel doesn't try to print two things at the same time, because obviously there's only one screen, but your kernel can be run across multiple CPU threads. If we look here, the definition for both deferred and default is in printk.c, so let's go back there. So ultimately, both the default and the deferred functions call into the vprintk_emit function. And what's interesting here is the vprintk_score function. So in the vprintk underscore store function, it does some stuff which is fairly irrelevant, like setting up buffers. It allocates some memory and then appends a message to a specific message list. If you dig a little bit deeper into the file, you'll notice this printk get next message function. So in the list of messages, when the system tries to get the next message, it will go down here, and then you'll see this line. If message may be suppressed, and the message should be suppressed, given the message's level. Let's check the suppress underscore message underscore printing function. So the message will be suppressed if the message's level is greater than your console's log level, and if you've not enabled the kernel parameter which ignores log level. So ultimately, the conclusion that I make from this is that even if you're on quiet mode, the kernel still does quite a bit of work allocating memory and whatnot and appending it to a list before it even checks if the level will be printed. This makes sense, given that I've measured a non-significant difference between booting with quiet and not quiet. In fact, technically speaking, booting with quiet actually took longer, but I don't really think that's anything other than statistical error. So I thought, as a little bonus, why not modify the Linux kernel? Let's see if we can block quiet messages earlier so they do less processing, and that might improve performance. So the first thing that we want to do is we just want to compile the normal Linux kernel and then boot it in a virtual machine. So to do this, once you're in your Linux directory, you can just do make def config. This will make the default configuration for building Linux. The configuration contains stuff like what sort of hardware Linux should support and that sort of stuff. So this is just the default one. Then you can do make -j and then the number of threads on your computer. This will compile the Linux kernel and it will take a while, so I'll be back when it's done. So now the Linux kernel is built. We can try booting into this using QEMU. Then we can specify the kernel. In this case, the kernel is just where it says here, which is just arch x86 boot BZ image. This is the compressed kernel image. Now let's just boot this normally without any kernel parameters. So you'll see that it prints a lot of stuff to the output, and it also kernel panics. The kernel panic is expected because we've given it no file system and we've not given it an init file, because what the kernel usually wants to do is after it's booted, it launches your init file. In my case, that would be systemd. In some cases it's openrc or runit or whatever. But in this case, we're not given a file system, so it kernel panics. But you can fairly obviously tell that it's not running in a quiet mode, which is expected because we haven't changed the code yet. We can provide kernel parameters by doing -- append and then the kernel parameter. So now, as you can see, it is booting, but it's a lot quieter. It's still kernel panics, of course, and a quiet mode isn't going to stop a kernel panic. You can see now that we can build the normal Linux just from like the Linux source code. Let's see if we can modify this. So interestingly here in the kprint.c file, we have the vprintk_score function. Now, how this works is your format string. What the kernel does to identify what log level it is, whether it's like a very important one or like a debug level, is it actually appends a header into the front of your format string. The function printk_parse_prefix will parse your buffer, and it will give you back the log level and flags. So let's take this skip check and then move it up a little bit. So right after it's parsed the prefix, let's paste the check-in, and then instead of doing the level here, we'll do the level here. Let's remove this may suppress call for now, and now let's see if this compiles. We need to go to here, because this isn't actually ever being called anymore, so we can just delete that variable there. Okay, so that did, in fact, compile. Let's try running it in a non-quiet mode. Yep, that's certainly not quiet. Let's try running it in a quiet mode. Interestingly, it was sort of quiet, but there was definitely an amount, or like some messages there, were being sent, even in quiet mode. To debug, let's just see if we block all messages on this path, what happens? How interesting. Now, the kernel prints nothing. Ultimately, I believe this is because only new lines have the actual header, while if you're trying to print something on a line which already exists, I'm not going to have that header. The header being the thing that I'm using to determine the log level. And judging by the code after this, where it's telling if something is a new line, and if something is continuing, I wouldn't be surprised if Linux, by default, has a way to tell if I'm currently printing on a line that was already flagged as being debug or whatever, and it makes sense as to why they would then want to defer this code to run later, because you don't actually know what the log level is just from reading the individual print k calls. But I don't want to leave you with nothing, so let's make it so we can change the text that gets printed. Now when booting... So yeah, we've even replaced the kernel panic message with YOLOs. So yeah, ultimately, it seems as if the Linux kernel does the check for log level later, intentionally, of course. And that's probably just due to design decisions made when they were making the kernel printing system, and there are probably billions of other reasons why they made it this way. So I hope you've learned something. See ya!